Okay, hello. I will try to explain this equation here, the theory behind it. But before, I'm sorry for my English be too slow. This is not my native language, and I'm sorry if I speak something wrong. Okay, but that's it. This is a six-dimensional geometry equation, space geometry equation. As you can see here, space and time as the velocity equation of Isaac Newton begins here. What is mean? This is velocity. Basically, it explains how the geometry of space-time looks like. But I have some doubts about it. I will talk about it later about this equation because I was thinking in a torus. How would be the speed of a on the inner circle of a torus if a torus was spinning uh, inward, inward, inward to its center. Okay, but let this for later. Before I explain this equation, let me shrink it. Left here, left here. Okay, I will explain some things about time travel and time machines. That was the subject I am studying for my whole life since I was 11 years old. So let's begin. I will draw here the earth. Okay, let me draw the earth here and we will have a better understanding of what is time travel. So let's draw America. Okay, Africa and Europe. Okay, so we have earth here, and we know that we have television transmissions going out of earth at the speed of light. This is CNN. CNN opens. Then this is the CNN close. So the CNN at this time here, the transmission travel to space, okay, at the speed of light. This transmission goes to the speed of light. I hope you understand what I'm saying. So imagine that we get a spaceship and we travel in three stages. We travel with a spaceship below the speed of light. Velocity is less than speed of light. Then velocity is equal to speed of light, and then if the velocity could be greater than the speed of light. Okay? There is three situations, and the spaceship has an antenna and a television, and he's watching CNN. Okay? So what happens in this situation? In the first situation, it happens that the transmission goes normally. The time the time for the transmission that he's watching on TV, the time is run positive, we can say that. But as soon as he came to get close to the speed of light, the transmission begins stopped. If he reached the speed of light, the transmission is stopped and get freezed because he is always in the same line that this frontal wave. And the interesting thing is that if he looked behind the ship and watched the Earth to see the Earth, he will see the Earth stopped in time. And if he used a loop, see, if he zoom in the Earth, he will see people stopped in time. So that's the theory behind time travel through the speed or velocity. So if the the guy surpass or trespass the speed of light, what will happen? The transmission will be rewinding from back to front, from the beginning from the final to the beginning. It will rewind. I don't know if this word is correct. I speak incorrectly. Sorry. Uh, um, so let me write here. Rewind. Time slow positive. Okay. So this is the basic basic concept about time travel. Okay. So let me explain. I will come back here later at the end to explain a peculiarity, something very specific about this geometry here that make me doubt about time travel. I will explain in the final. Okay, let's continue. Now let's get to this equation. This is basically Newton. In this part is where the actual science is stopped. It's the Lorentz transformations for speed. You can check this on Google. Lorentz transformations for speed is basically it's not equal to this equation. This is a compact version of Lorentz transformations for speed. Okay? But basically is this. This part is what I made, but it's not completely mine too, because I borrowed this from this part here, this part below. I borrow from Ehrenfest, the paradox of Ehrenfest, but I will explain exactly this equation. This Lorentz transformation I will not explain completely, okay? This part is Feigenbaum. This is a U, sorry my letter, Feigenbaum constant. Or it's called bifurcation period. Okay, I will explain everything here. But first, I will show you one situation. That's the situation. Lorentz transformations are from the special relativity or restricted relativity. They are explained like this. They are usually for straight lines, straight velocities without curves. Okay? So straight vectors. I don't know even if there are curved vectors, but for straight lines, straight trajectories. So there is a situation when we have straight lines as a result, but we don't have straight lines as a propulsion. And that's where my equation comes in, and Lorentz transformation don't explain. Okay, let me try to show you. So here's the boy without his head, sorry. He's walking on skate on one direction, and he closes a scissor in the same direction that he's walking on the skateboard. Okay, so when he closed the scissors, sorry, the point here is that the scissors ears are going to close in curves. Will rotate. The edges of the scissor will rotate, but the resulting velocity is a straight line. So you should calculate this with Lorentz transformations for speed, right? With special relativity. But the equations for special relativity doesn't fit this situation, these scissors. So basically, I made my own equation. That is this one. So what happens is that, let me explain first this equation. You get a scissor and you put on a Cartesian plan, okay? And you make a circle around it. I hope my circle goes okay. Oh, it's the better circle I made. So, if I close the scissor here, it will go to this direction, and the other edge will go to the opposite direction, and it will close here at 45 degree, right? And we know that here at 0 degree, here is 90 degree, or P, I don't know how to say this, P divided by 2. So this is P, in the middle will be P divided by 4. So the speed of the cutting edge of the scissor is equal the speed of the cutting edge is equal to 4 so divided by p plus the speed of the edge, and that's this equation here. This is the classical equation basically, and I just transform this classical equation in a relativity equation. You can check in Ehrenfest paradox. You can check Ehrenfest paradox for explain that P on relativity is like this. Okay, it's exactly like this equation. So you should represent P like this. And V E is the same as W double plus radius. This is the same thing. This is the same equation. So what happens if you sum this velocity of the skate plus added added to the velocity of the cutting edge of the scissor? You trespass the speed of light. And if you trespass the speed of light, we get that situation about looking back on Earth. It will rewinding. The time is runs in a opposite row of time. So basically that's the theory, but it doesn't finish here. Oops. I will erase this first. Erase. Oh, I have to erase here because I need space. Okay. So the point is that okay. Isso aqui, this one. Okay. Now, why I put Feigenbaum constant here? Let me explain you one thing. This Lorentz transformation for speed is a unidimensional movement. Okay, it uses one-dimensional movement. This equation for the scissor, for example, the next, it uses it's a angular velocity, so it uses as it is a rotation. It uses two dimensions. So we added more plus 2 dimensionals. So why I add this, and we have here 3 dimensions, okay? Why I had to add more dimensionals or more equations to that equation? Well, think about it. Think about this situation. Imagine that I'm in my life I never encounter a version of me older that had travel to the past and meet me in my past, okay? I never meet myself. But now I will get a time machine and I will do this. I will go back in time and see myself in the past. So let's draw the situation. I have one guy that is me now that doesn't does not meet myself. Doesn't meet myself. And I have a guy that is me on the past. He did meet myself. Okay? I am this guy here. And I travel to past and meet myself younger. But I know that I didn't meet myself young. What happened here? What happens is that we created another dimension. We jumped from one three-dimensional universe to another three-dimensional universe. It's a copy. But how can you explain that mathematically? The only way that you can explain that mathematically is adding Feigenbaum constant plus an origin. What is Feigenbaum constant? Is the duplicity of period. It's basically a way to represent it. It's a straight line that gets double, and this double gets double, and keep doubling in for infinity. And this gives a notion of timelines and extra dimensions and so on. So basically, this Feigenbaum constant plus this 2a, we can add more 1, 2, 3, more 3 dimensionals here, and we have 6-dimensional universe, a 6D universe. But what is a 6D universe? Think about it. In a 3D world, we have a cube. In our 3D world, okay? And this cube is made of 6 2D squares. So a cube is made of 6 2D squares, but it is made of 6 2D elements. So a 6-dimensional object is made of many or infinity many 5D objects that are made from many 4D objects that are made from many 3D objects. So in the final, you have that a 6-dimensional universe. It's sort like a constant of Feigenbaum that each option the universe can take, it will subdivide it in a 3D world. So in a sequence of time where this is t0, this is t1, and if you trespass the speed of light, you jump from this from one world from one world to another world. Okay, that's the basic idea. But now let's get back to this guy traveling. Okay, uh, sorry. Let's get back to this guy traveling above the speed of light. Imagine that I this is the problem. So, what's the catch? This look perfect, right? Looks perfect, but it's not perfect. There is a catch here. There is a problem. The problem is if the guy here that is above the speed of light tries to make his turn to Earth, what will happen? The Earth will speed up proportionally proportionally as he rewinded when he was going away from Earth. So sorry, in the end he will get to the same point he was. Did you get it? So what's the catch about it? The catch is that these structures here in 6 dimensions only works if each new created universe create another universe rewinding. So I have one universe going forward, another universe rewinding. Uh, one universe forward, another universe rewinding. So each time I trespass the speed of light in one universe, I go to a rewinding universe. So these events will be opposite. So he goes in front of him, it will go into the past, and behind him, behind the ship, it will go forward in time. So if he goes away from Earth, trespasses speed of light, and go to another dimension, 3 dimension that was rewinding, what happens? What happens is that when he turn back, make his turn back, it will be rewinding. Okay? Did you get it? So that's the catch. That's the catch. The theory looks perfect, but without this point here, everything breaks up. And how we can prove that, how we can know that if we trespass the speed of light, if we could do this, still we had to believe that the another universe must be rewinding, so then we can travel to time, through time. I really wish that this could be true, uh, but I don't believe it. The other thing that I should explain, I think it is about the torus, right? The torus, if you have a torus, a Tipler torus, right? And keep spinning. What happened in the middle? So, basically, this torus has the same equation for this speed here in the center than the scissor. But the difference is that the scissor is only one dimensional, I mean one dimensional, because it's 2 dimensional but is isolating another dimension. Here in the torus is 3 dimensional. So I would only remove this, you put this here. That will be the Tough's equation, or the geometry of space-time would be like this. That's what I will do, because I multiply this pi because it has a scissor here, it has a scissor here, for example. It's one way, so I multiply per 100 degree by pi to fulfill the whole circle. So I multiply the speed by here, or just simply, no, yeah, it's like that. Simply remove everything here. I don't know. I'm just testing. I, I didn't think about it because this idea came for me today. So it's something like that. Uh, Maybe it's this plus this, but it's not. Only double basis A. Only double plus R. I don't know. I have to study to make sure. Okay, thanks for watching. I'm sorry about my English. It takes half an hour, but that's all I can explain. I'm sorry, just very sorry about my English. I should train better. Okay, thank you very much.